Hi, this is Dr. Arman again. We're going to look on the Thermal Engineering MEC 551 for Chapter 5, Refrigeration Cycle. So this is the first section for the refrigeration cycle. There are going to be about 4 sections for this chapter. So refrigeration system, heat transfer is usually experienced in direction of decreasing temperature. Reverse process need a mechanism. So the purpose of the refrigeration cycle is to have a heat transfer from a chamber so that the temperature inside is reduced to below that of its surrounding. There's also the application of the refrigeration cycle can be adapted to suit with the conditions. For example, if it's going to be taken the heat from the refrigerated, so which is the desired output as the for the cooling process, it is called as the refrigeration cycle or refrigerator. So, but if the other way around, if the requirement as to heat up the chamber or of the spaces, then it is called as the heat pump. So the space inside the chamber is said to be cold, and the machine used to achieve is called as the refrigerator. But if it is the other way around, then it is called as the heat pump. So refrigeration process consists of the continuous circulation of the working fluid through a cycle of the processes. It uses working fluid called as a refrigerant, where the magnitude of the heat removed from the refrigerated spaces called as the QL, where the temperature is TL. The magnitude of the heat rejected to warm space at temperature of QH. So this is a QH, and then the temperature of the rejected to warm space is called as the TH. So the mechanism or the component to use for the heat remove from the refrigerated spaces called as the evaporator. And then the heat rejected to the warm spaces by using the condenser. Okay, so the refrigeration has many practical applications in this modern life. For example, at your home, as for the domestic refrigerator to preserve the food, freezer for making ice cream, extended storage of foods, example for the meat, vegetable, ice cream. As for the air conditioning process for comfort and hygiene, and as well for the cryogenic in a very low temperature for the purpose of the gas liquefaction and the scientific research, and as well for the air conditioning for the heat pump process. The heat is absorbed from the cool region with the temperature Tc. So through the evaporator. So the process is heat absorption from the refrigerated spaces, and then heat will be rejected from the cycle, from the refrigeration cycle to the warm region at temperature TH through the condenser. So the temperature for the condenser must be higher than the temperature of the surrounding. Okay, so in order to that, thus the heat will be rejected to the surrounding. So the temperature, the Carnot refrigeration cycle is using the refrigerant as a working fluid. When we look at the temperature entropy diagram, so this is a temperature entropy diagram, TS diagram, and this is a TS curve. So what we see here is actually the process 4 to 1, which is heat absorptions from the refrigerated spaces, and then the temperature TH for the heat rejection to the surrounding. As we can see here, the temperature TH will have a higher pressure as compared with the pH higher as compared with the PL. So in order to increase the pressure from the evaporator to the pressure for the condenser, so that the condenser can reject the heat to the surrounding, so a compressor can be used to compress the working fluid from PL to pH, from the pressure of the evaporator, operating pressure of the evaporator, to the operating pressure of the condenser. Okay, so the compressor required an external input power, which is W dot C. Okay, so the heat will be rejected in the condenser, and the power for the compressor is WC, which is the process from state 1 to state 2. And then after the heat rejection at the condenser, the cycle has to go back to the evaporator, but the pressure is high, so that a turbine has to be used in order to expand the working fluid. So the turbine will expand from the pressure pH to pressure PL, where the pH is the condenser pressure and PL is the evaporator pressure. So as you can see here, there are a few lateness in terms of the operating conditions. But the Carnot refrigeration cycle is the highest coefficient of performance, or the highest efficiency that can be obtained for the operating condition for the refrigeration cycle. So this is the processes that happen in the temperature entropy diagram. And there is one additional, which is called as the pressure enthalpy diagram. So this is a pressure enthalpy curve. Okay, then this is the operating pressure. Okay, so from the AB for 1, so which is heat is added to the refrigerant from the co-region, or heat absorption at the evaporator. AB32 is a heat rejection from the refrigerant to the warm region, and then the net area 1, 2, 3, 4, 1, 2, 3, 4 is a net heat transfer from the refrigerant. So the net work done is the work done by the compressor minus work done by the turbine. As for the temperature entropy diagram from the state 1 to state 2, and for the entropy diagram, pressure enthalpy diagram from the state 1 to state 2. Okay, so in the temperature entropy diagram from state 1 to state 2, the process is isentropic. So this is an ideal process where the process is adiabatic, and then no heat transfer occurs, and it is a reversible. Okay, but there will be change of the enthalpy from 1 to 2, and then 2 to 3 is the heat rejection, Q dot H. 3 to 4 is the expansion in the turbine. Okay, sorry, this is that one. So the expansion in the turbine, the enthalpy will be yeah, like that. Okay, so this is a state 3 and this is a state 4. Okay, and that is arrow for the process. And then finally 4 to 1 for the process heat absorptions. So the value for the cycle efficiency is no more suitable for the value of the working of the refrigeration cycle. So the parameter to express the performance of the refrigerator is known as the coefficient of performance, where it is referring to the desired effect as compared to the work input. So if you are analyzing for the Rankine cycle, it is more toward the work input or work output that produced by the cycle. So the term used for the evaluating of the performance for the refrigeration cycle is known as the coefficient of performance. So the coefficient of performance is the ratio between the desired output divided by the required input. So the desired output for the refrigeration cycle is the cooling effect, or the QL, which is referring to the temperature entropy diagram back again. So this is the temperature, this is the entropy. Oops. Supposed to be this. Okay. This is high pressure. This is low pressure for the. Okay. So this is a 1. Okay, this is a compression 2, and then 3, and then go back 4. Okay, so this is a QL, and this is a rejection QH. So looking at this chart, looking at this diagram, the QL can be simplified as TL, and then the work net work output WC minus WT as TH minus TC. Okay, so which is, this is the TH and this is the TC. As for the heat pump, the desired output is the heating effect, which is QH, and the required input is the net work from the difference between pump power and the turbine power. So this is an example for the class that you can do later on. A steady flow Carnot cycle use the refrigerant 134A as the working fluid. The refrigerant changes from saturated vapor to saturated liquid at 30 degrees Celsius in the condenser, and as it rejects heat, the evaporator pressure is 120 kPa. show on the temperature entropy diagram, sketch a schematic diagram, show on the processes on the temperature entropy diagram that shows the saturation line, and determine the coefficient of performance, the amount of the heat absorbed from the refrigerated space, and the network input. Okay, so but however, the most ideal is the reverse Carnot cycle or Carnot refrigeration cycle, but we can consider that it's a perfect cycle, but in reality there are lackness in the Carnot cycle, which is, in order to maintain the temperature at Tc, the refrigerant in the evaporator must be slightly lower than the temperature of the Tc prime, which means that the temperature for the absorption must be lower, which means that the temperature for the evaporator must be lower than the temperature from the cool region, so that the heat will be absorbed to the evaporator. Similar to the condenser, the temperature for the condenser must be higher than the temperature for the surrounding. Okay, so that is one. And the another one is that, yeah, so this is can be shown in the temperature entropy diagram here. So as for the temperature for the cold region has to be higher than the temperature for the systems, for the refrigeration system, and as well the temperature of the warm environment must be lower than the temperature for the condenser. Okay, so thus the coefficient of performance will be adjusted in become like this. Okay, so that the coefficient of performance for the Carnot cycle will become as the temperature referring to the condenser, referring to the cold region, and then we're referring to the hot region. Okay, and then also the departure from the Carnot cycle, the process in the compressor from the 1 to 2 begin in the vapor dome with a fluid gas mixture for the compression. So what does it mean is that the beginning of the compression process will happen in the mixing regions, where there will be some fluid droplet in this mixture that can damage to the compressor blade. Thus, this wet compression must be avoided by starting the state 1 in or on the saturation line. So which means that on the saturation line, which means the process must be pure dry when it is compressed in the compressor. So the only possible is that the saturated vapor has to be achieved in order for the fluid to be compressed in the compressor. So the fluid must be ensured to be in the dry compressions. Third, the expansion process through the turbine produces a little work output as compared with the large power input by the compressor. Therefore, to have a turbine compartment in the refrigeration system is not viable and is high in cost. And as well, when you want to do the maintenance for the refrigeration cycle, you require to maintain the turbine. So maintaining the rotating equipment is not easy. So thus, in order to save on the capital cost and operating costs and the maintenance cost, the turbine is normally replaced by an expansion valve, which is cheaper in operation and much cheaper than the turbine. With these three conditions, a new line for the refrigeration system can be redesigned. So for example, this is a refrigeration system that be used for the domestic refrigerator, where it is contained of the evaporator here, okay, and then this is a compressor. The flow goes to the compressor, the evaporator, which is the absorbed heat from the refrigerated spaces, and then compress in the compressor, giving the hot gas line, where this hot gas line supply the refrigerant, let's say 1R134A, and then go into the condenser, and then the heat will be rejected to the surrounding. And in the compressor, I missed this one, which is the work input in the compressor. Okay, and then the heat rejected in the condenser with the QH. And then we go back to the expansion valve before it expand the heat to the evaporator pressure. Okay, so this is the expansion valve. So this is a domestic or household refrigerator. The location is depend on the design. Some of the design, the the evaporator located at the bottom of the household refrigerator, and then the arrangement will be a little bit different than this. But normally the evaporator, which is used for the frost area, is located at the top of the household refrigerator. Okay, and then the compressor is located here. Then this is a condenser. This is a drain for condensing. Okay, and this is the evaporator coil. Okay, and this is the expansion valve somewhere. It should be around here. Okay, all right. Okay, so the component for the household for the refrigeration system, it has to contain of the compressor, which is to provide a driving force for the entire system by drawing a low pressure from the refrigerant, by drawing low pressure of the refrigerant in the evaporator and compress to the pressure that exit with the higher pressure, so that we go with the higher temperature before it enter to the condenser. A condenser, which is it will exhaust the heat from the system by virtue of the heat transfer across the temperature gradient. So we have gone through the fourth chapter before, which is heat exchanger chapter. So the condenser and the evaporator is using the principle of the heat exchanging process. So by adapting or using the heat exchanger chapter previously, actually you can do some design integration in order to complete for the refrigeration system. The refrigerant in the condenser is at higher temperature than the ambient temperature, so thus the heat can be rejected to the surrounding. As the compressor, so this is the work output, work input, which is WC. Okay, and then expansion valve is to allow the refrigerant to expand in the control process such that it will exit the valve with the low quality in the liquid vapor region. So there is no power input, power effect in the expansion valve. So thus the W dot is equal to 0. So which means that m dot can be maintained, but the enthalpy will become 0. Okay, so thus the enthalpy at the H3 will be equal to enthalpy at the H4, but still the entropy will be not similar. Okay, from the enthalpy S3 is not equal to enthalpy S4 because the temperature is different. So the evaporator absorbs the heat from the cool space by virtue of the temperature gradient similar to the condenser, and the process is Q dot in or Q dot C. Okay. So this is a schematic diagram for a refrigeration for the ideal refrigeration cycle. So process 4 to 1 is the heat absorption from the refrigerated spaces by the evaporator. 1 to 2 is the compression process, isentropic compression process in the compressor. 2 to 3 heat rejection in the condenser to the surrounding. 3 to 4 is the expansion process in the expansion valve. Okay, so this is the summarize of the processes that I mentioned before. So 1 to 2 is the isentropic process. So with the isentropic process, and then it is started at the saturated vapor. So what does it mean is that the process 1 to 2s, which means that the isentropy S1 is equal to S2. So there is no entropy change. Isentropic process adiabatic and reversible. So there is no heat exchange. And then the heat transfer from 2s to 3 in the refrigerant at the constant pressure in the condenser. 3 to 4 throttling process in the two-phase mix where H3 is equal to H4. And then refrigerant 4 to 1 is the heat absorption in the evaporator at a constant pressure to the saturated vapor state. Okay. And I want to highlight that there is arrow missing in this slide. Okay. So from process 1 to 2 is isentropic process where S1 is equal to S2. The power output, the power input here, this is a WC, which is equal to m dot times H2S minus H1. And then 2S to 3 is the heat rejection from the condenser to the surrounding, QH, which is m dot H3 minus H2S. So this is going to give you a negative value because heat rejection from the system to the surrounding is negative. And finally, process 3 to 4 is a throttling process across the expansion valve where there is no power. W is equal to 0, so H3 is equal to H4. And then finally, this is the heat absorption from the refrigerated spaces, Q dot C, which is equal to MH H1 minus H4. The pressure enthalpy diagram. So process 1 to 2. So this is a W dot C, which is m dot H2S minus H1. And then heat rejection H2S to the 3 minus H2S. The value you can value for the enthalpy and entropy you can refer to the property table or property chart. Okay, and then this is a process H3 is equal to H4 where there is no power effect in the throttling valve. And then refrigeration sections in this 4 to 1 which is Q dot L equal to M dot H1 minus H4. Okay. So QL is the heat extracted by the unit mass of refrigerant during the evaporating process, and then QL capital, which is this one, required per unit rate of the heat extraction in kilowatt by the refrigerant in the evaporator. So this is a unit kilojoule per kilogram. And then refrigeration capacity or cooling capacity, QRC, is the actual rate of the heat extracted by the refrigerant in the evaporator. In practice, the refrigeration capacity of the equipment selected is often slightly higher than the refrigerant load. Okay, so it's higher than between 5 to 10%. So because this is a manufacturer specification, are a series of the fixed capacities. Occasionally, equipment that can be selected so that capacity is just equal to the refrigeration load required. So if it's just equal, then through the years of operating, the efficiency for the refrigeration will, or the heat exchanger will reduce due to the few problems, like for example the falling effect or something like that, and the dusty of the operating condition. So that's the performance, overall performance, and then the refrigeration capacity will be reduced if you using the similar capacity load is equal to the refrigeration load equal to the refrigerating capacity. In order to analyze the vapor compression, the rate of Q in is given by this equation, which is I already mentioned in the previous slide. Okay, this is a per unit mass, but Q dot in is also equal to M dot H1 minus H4. Where terminology M dot S is the mass flow rate. Okay, so this is a mass flow rate. And then Q dot in is referred to as a refrigeration capacity, and it is normally used in terms of the kilowatt. Another common unit to use for the refrigeration capacity is known as the tone of the refrigerations. For the refrigerant leaving the evaporator, then it is compressed to the relatively higher pressure and temperature by a compressor. So the compressor power input is given by this equation, which is W dot C equal to M dot H2 minus H1. Okay, for the isentropic, W dot C isentropic M dot H2S minus H1, and then W dot actual, this is a W dot actual. Okay, Q dot out, refrigerant passes the condenser, where the refrigerant condenses, and there is a heat transfer from the refrigerant to cool the surrounding. For a control volume enclosing the refrigerant side of the condenser, the rate of the heat transfer from the refrigerant per unit mass is given by these equations, and also can be rewritten as the Q dot H or Q dot out equal to M dot H2 minus H3 or H3 minus H2. But this H3 minus H2 will give you this is a negative value actually. Okay, and finally the refrigerant in the state 3 enter the expansion valve and expand in the evaporator. This is usually the process is there is no power involved, so thus H3 is equal to H4. The refrigerant pressure decrease in the irreversible adiabatic expansion, and there is an accompanying increase in specific entropy. The refrigerant exits the valve at state 4 as two-phase liquid vapor mixture. Okay. Thus, the vapor compression system, the net power input is equal to the compressor power. Since no power involved in the expansion valve, so the net power input is equal to the power required by the compressor. So the performance for the vapor compression for the refrigeration system is the cooling effect. So the cooling effect is Q dot in. Okay. Then the coefficient of performance is the desired output divided by the required input. So from this equation, it can be simplified by the enthalpy change. Enthalpy change in the evaporator and enthalpy change in the compressor. The refrigeration capacity decides the mass flow rate of the given refrigerant when working under specific condition. So the refrigerant capacity, the mass flow rate of the refrigerant is equal to the refrigerant capacity divided by the refrigerant effect per unit mass. Alright, so this is your first assignment, which is the due date is on the 30th of May 2020. Okay, by 5 p.m.